Welcome everyone to our Support Vectors meetup. This is July the 24th. It is 7 p.m., 7:15 p.m., or well, 7:18 p.m. here in California. And I suppose it's pretty late night on the East Coast and early morning in India, and obviously different times at different places. Today, we have a very interesting topic, which is about the application of transformers, one of the first successful application of transformers to time series data. For our speakers, we have two illustrious speakers. I would like to introduce Shrikant Chanda. He has graduated with Masters in Computer Science from Columbia University and currently is working in AT&T Bell Labs. I would also like to introduce his father, Lakshmi Narayan Chanda, who's part also of Support Vectors actually, and and a PhD in theoretical particle physics. So we have rarely do we have the pleasure of having speakers, father and son combination, and so it's a privilege to have that. With those words, I'll yield the floor now to you, Shrikant.
Thanks, Asif. Hi, everyone. It's great to be here. It's always pleasant to come back to Support Vectors. Um, I don't know if a lot of you know, but I did an internship here at a point a couple of years ago during COVID, and it was a nice stint. And yeah, today I'm excited to talk about this paper, which is on time series forecasting. It is something that I've been working on or I've been starting to explore at my job at AT&T Labs. And when I was discussing with my dad and Asif, we figured we could do a paper reading session for this particular paper. So, just another introduction about me. Like Asif said, I graduated from Columbia, and I'm now working at AT&T Labs. I predominantly come from a machine learning background, because even before Columbia, I was working at Intel for a year and a half, and even before that, in my undergrad, I was mostly doing machine learning and electronics. So it is exciting to be here, and I'm looking forward to presenting this with Asif and with my dad as well. So let me start sharing my screen. Okay, can you see my screen?
Yes, we can.
Okay, so the paper is titled A Time Series is Worth 64 Words, Long-Term Forecasting with Transformers. Essentially, this paper is trying to is trying to propose an efficient transformer model that can do accurate time series forecasting across multiple variates. Um, and the idea is to use something which has been happening in NLP and in the development of foundation models, in the context of NLP, to use it for time series data and do a similar process wherein you can get predictions for time series data. um, in a nutshell, what is being proposed is an efficient transformer design for multivariate time series forecasting. And through this, they also propose an efficient way to do self-supervised representation learning, where you end up using lesser compute as opposed to end-to-end supervised learning. And a bit of a spoiler for this paper is that they're essentially using some amount of past data, which is called the context window of time series, in order to make predictions into the future. And through their analysis, they see that if you chunk certain segments of time in the past and then feed it to a transformer of inputs which are of size 64, you end up having an accurate representation of what the modeling of time series data in the future would look like. And thus the play on the name, which is A Time Series is Worth 64 Words. um, So this is how I'll be structuring most of my talk. I would start off with a brief introduction and how past work in this space has been working. I'll give an introduction as to how the concept of patch in this paper, which is discussing patch TST, works. There are some key features here, which is called the concept of patching and the concept of channel independence, which I will brief about. I'll also talk about what the advantages are compared to the previous work in this similar domain, and also other linear models that have tried to do time series forecasting. I'll then jump into the methodology, speak about the model structure, and how representation learning is actually happening in this work, which also seems to be the key novelty this paper talks about. And finally, I'll talk about the experiment and the description on what sorts of data set they're working on. How does it compare with benchmarks, and what is their novel? What is essentially their point of view at the end to say this work is, better than the previous or other linear models. Um, Before going any further, let me just read out this summary that the reviewing committee gave about this paper. This paper applies transformer to long-term forecasting problems of multidimensional time series. The method is simple: take channels independently, break them into patches, and predict the patches into the future using a transformer. The main advantage of this paper is that previous papers have applied transformers to this problem, but it has always resulted in weak performance, being even beaten by simple linear models. Whereas this paper has found a way to apply transformers successfully and beating previous methods and linear approaches. Um, so, the concept of trying to do time series forecasting in this paper uh, comes across through an idea where they try to given an input time series, instead of looking at individual point-wise values, numerical values at each step, and then feeding it into a deep learning module, the idea that they try to do, they work on, is by making it into patches. When I say patches, what it means is you're trying to extract the local semantic information, not just from one point, but also its neighborhood. And some past work in this area has been in the work such as BERT, and where inherently in NLP, when you're trying to do some sort of next word prediction, what you end up doing is, when you're looking at the past data, you don't look at character wise representations, but you look at word, which inherently can be translated to a patch in the context of time series. So patch in itself is something that has been worked on in the past in various other contexts. Obviously the most predominant one is BERT. Also in vision, it's been worked on a lot, where you're treating an image and splitting it into 16 by 16 patches before feeding it into a transformer model. So patch as a concept has been worked on in different aspects, but it is one of the few first times where it is being used for time series forecasting. um, Even for time series forecasting from a transformer based approach, there have been some implementations such as logtrans, autoformer, triformer. But all of these, in a nutshell, they, while they do make an implementation of transformer, they don't make a consideration of including these patches across time steps. And so then you lose out on the semantic information, making accuracy much lesser. So without jumping too much into depth on each of these models, i I have just mentioned the main drawbacks of each of these models, which I will probably try to just delve into a little. So in logtrans, it avoids a pointwise dot product between key and query. Wherever they're looking at the attention mechanism, it ends up not looking at the value across a patch. It ends up looking at only one single time step, and that's a drawback of logtrans. In autoformer, it uses autocorrelation to get patch level connections, but given that it's a handcrafted design, it doesn't take into account all the semantic information within the patch. um, Similarly, in Triformer, it essentially proposes a patch attention, but only to reduce the complexity of the query within the patch. So it doesn't really treat the patch as an input which uses semantic information across time steps. All of this basically is to say that, in this particular paper where you're using a patch concept in time series data, it seems to be the novel approach leading better accuracy. So, what exactly is patching? Like I've mentioned, it's essentially segmenting the time series into sub-series data. And the idea is you want to extract local semantic information, which will not be possible if you look at only single time steps and then try to feed that into a transformer module. So, this is just a rough sketch that I have. Let's say you have these 8 time steps. It's a bad drawing, but let's say you have these 8 time series points of floating point numbers. What patching essentially means is, if you have, say, the patch size is equal to 4, and say you have a stride of 2, which means you're jumping 2 steps every time you're considering an input to the transformer. So 4 and stride of 2, these are the kind of inputs that you end up having, which are then sent into the transformer. So you end up having the first element, second element, 3, 4.3 as the first patch. Then the second patch would start from 2 steps away because it's at a stride 2. So you have 3, 4.3, minus 5 minus 5, and then 6.1. Similarly, you move 2 more, and then you take 4, you move 2 more, and you take 4 more. And eventually, if you have values which are not of the exact multiple of the number of patches, you end up padding with the last element. So this is essentially what patching is. You're trying to take subseries of the inputs, use that as input to the transformer, because that has a richer idea of what the context window looks like. When I say context window, I mean the look back history, which is the input to the transformer. The other key feature is channel independence, where as opposed to looking at, if you're looking at multivariate time series, instead of trying to make a representation where the future of one of the variables is affected by the past of the other variable, this paper tries to essentially split them all up and make it in such a way that the predictions of one particular time series is dependent only on the past of that particular time series. And the idea that it's trying to convey is, given any time series, it intrinsically has the patterns of trying to generate the patterns which can then be understood by the transformer, which can then relate to what the predictions should be. And you do not need the reference from another time series to affect a particular time series, a particular variable's future points. So each channel contains single univariate time series, and then you eventually share the same embedding and transformer weights across all series. So if you have multiple channels, essentially split it, treat each of them as inputs to the transformer, and have outputs which are only dependent on each of these univariate samples. Right. So these are the essential two concepts. Essentially, have patches where you're taking multiple chunks of input instead of just one. And the other one is, if you have multiple variables which you're predicting, forget the remaining variables when you're predicting one of the variables. So fairly straightforward concepts, but it seems to work much better than every other previous model that had been proposed. So some advantage of this is, clearly there's a reduction in the time and space complexity, because the original transformer, if you had
Shrikant,
yeah,
uh, uh,
yeah,
sorry, hey, this is Ganges. So I have a quick question on
yeah,
that the channels. So to
yes,
put things in perspective, can we assume that okay, each channel as, let's say, for example, I have a temperature, pressure, vibration as like a three different variables, and those will be considered as channels, right?
yeah,
Okay. So then when we feed that into patching each one of them as like the patching model, what you described earlier, and
mm-hmm.
then it use the same embedding model, and then it is going to have uh, their weights based on the transformation, whatever it's going through the neural network. Is that right?
Yes.
Okay. The how the output is going to be considered? Like then do we? So what if suppose that the two variables are interdependent?
So if they are interdependent, even if they are interdependent, the idea is that by looking at just one of the variables, you are able to capture all the information required to predict its own future. And if they are even if they are interdependent, there is never a place where the transformer is trying to look at the second variable and then use that information for the first one. That is just not happening in this paper.
Okay. Okay.
Right. So the advantages of this are, firstly, there is a reduction in the time and space complexity, because originally, if you were taking just the pointwise variables, pointwise elements as inputs, and you had say n samples, your the complexity of the time and space would be O of n squared, because you're considering each of these tokens, each of these inputs as tokens. Whereas after pre-processing with patch size and stride, you could reduce it by the factor of the stride, like we saw here, where you had a stride of 2. So you essentially factor it, this eight segment token, into 4 elements, which is reduced by a factor of 2. So there is reduction in time and space complexity. And the paper also says that if you set a patch length of say 16 and stride of 8, the training speed becomes almost 22 times what it usually is on large data sets, because you almost have a quadrupling effect on the reduction in complexity. And because of this, you are also able to look into a longer look back window, because you can now look at greater lengths of.
Lens of.
Is there an echo? Yeah, so
Right.
there is also a longer look back window that you can look into, because the idea is there a way, I mean, if you are having higher space complexity, it means that you're trying to answer the question, is there a way to avoid throwing values while also maintaining a long look back window? And the answer to that is simple, that if you have a patch where you are considering each of these patches as one token, you're essentially doing that by reducing the complexity and looking at longer look back windows, which results in higher accuracy. Another advantage of this transformer approach is the fact that there is a capability for representation learning. What this means is you can have a transformer model which has been trained on one data set, um, um, and if you have an accurate representation of what these time series modeling looks like, you can then fine tune it to another data set and then see that it actually works well, which I'll be showing in the results in the future slides. Um, this is just an intuitive picture as to how the patches are generated and what the input to the transformer looks like. So in this paper, they talk about two particular approaches, where you have length, the look back window of 512 elements, where you're essentially looking at 512 elements, and a patch, then the patch size of 16 with a stride of 8. So what this means is, if you have this sort of a this sort of a setup, you end up having 64 patches each that move in such a structure, where you have a stride, you have an element, you have the tokens being generated, um, and each of those inputs are then sent into the transformer in this format. um, so to get into the architecture a little more in detail, firstly you have the input, which is a univariate time series, because we're doing on a per channel basis. And for each of these channels, you're doing this patching process, where you're having either 64 patches in general, because that is the default that they're using in this paper, but it can be varied based on your patch size and patch length. You have these multiple inputs which are then being sent as inputs to the transformer. There's also a positional encoding which is happening. Uh, you have the transformer encoder. So at this point, the shape of the data is essentially d cross n, where firstly, when you have each of these look back windows of say length L, and you have a patch of size P and number of patches N, your input essentially is of the shape P cross N, because you have P number of patches and N is the patch length. And the paper essentially tries to do a projection into another dimension D, which they later use and reveal as to be 128. And that is being input into the transformer, which then follows a structure such as this. And then you have the predictions being made after flattening, etc. But the main thing that I want to convey through these two structures is how this paper suggests the architecture for self-supervised learning and supervised learning. Um, till now, I think we're clear on the fact that there is patching, channel independence, and there is an architecture for transformer which is happening based on some representation spaces which are then modified through projections. So firstly, there is the supervised approach where you're trying to have each of these patches, and the transformer is required to auto regressively predict what the next patch would be. This follows the simple structure of trying to do mean square error between what is the prediction, what is the target. Whereas in self supervised, what happens is you have a different structure where you are having all of these patches, and some of these patches are masked, and then the task of the transformer is to recreate these patches. And now the reason I'm talking about both of these architectures is because in the paper they talk about an approach where they do pre-training of the transformer using the self-supervised approach, where they have non-overlapping patches. So given a time sequence, they have patches which are non-overlapping, not overlapping each other, and then they try to predict what the next patch or the masked patch is. And through that structure, they have a transformer which has been seemingly trained to a good degree on trying to predict time series data in general. And then finally, they then use a supervised approach to fine tune onto other data sets or even the same data set with more accuracy, where in which case they're actually doing the prediction by looking ahead and seeing if the prediction matches the target. So that is the key idea through these two diagrams that I wanted to convey.
Question?
Yeah.
Could you go back to the prior slide? Yeah. So in the self-supervised case,
Right.
are they not comparing or calculating a distance or a loss relative to the prediction that was made for the missing patch relative to the actual patch? I'm just
They are.
having trouble understanding how that is self-supervised versus actually supervised.
So in self-supervised, you're essentially using the same. You're not looking ahead into any future. You don't have a target variable which has been explicitly set. So you have these the same input, some of these patches randomly are masked, and then you're trying to do the same error calculation and then do the prediction of these masked patches. And in supervised, you have these future targets which are more explicitly considered as targets, and thus it's called supervised and self-supervised.
Oh, I see. So the main difference being that the predicted data is or isn't part of the training set. Okay.
Right. And this is more, you can consider this as an auto-regressive method. So you have these inputs, you're using the same data the same data extension as the prediction, and then you're trying to compare between the target and predicted. Is that clear? Did that answer your question?
I believe so. I mean, you're still calculating a loss relative to the content of patches. The only question is the patch a future patch which wasn't in the current context of the transformer, or whether it is in fact internal.
Right.
Yeah.
Yeah.
Okay. Yeah.
So in other words, the master patch is your label, basically. Like that is what we are going to predict, I believe. And in the self-supervised, Shrikant, the stride is 0, right? Because we don't want to kind of like have any overlap.
Yeah, that's right. They don't want to have overlap.
No, stride is equal to the patch length.
Equal to patch length, yes. So you ensure that there is zero overlap, meaning you're going the full length of the patch.
Right.
Full length of the patch.
Your stride will never intersect a patch. Right. You're always going to go by patch size.
The reason for that
there is zero stride.
No, the stride is equal to the patch length, because if the stride,
correct,
the thing with masking is, if you have a stride while you do masking, there would be a case where the next patch may have some information about the masked patch, and then you're kind of biasing your training. Whereas if you have the stride, which is completely, if you have two patches which are completely different from each other, and then you're masking some of them, then your task is more difficult for minimizing loss, because you don't have any overlap of information, given that there is no overlap of data, because stride is
Right, right. If there was overlap, it doesn't, masking would have seen the data earlier, actually, because there was an overlap. Yeah, makes sense. There shouldn't be any overlap for the masking case.
right. Okay, so this is more of a just more elaborating more on how the self-supervised versus supervised training happens. They've also provided the GitHub for this code. So in that, they have specified something called the head type. So they use a similar network architecture in both self-supervised and the supervised training, and the only difference is they have a different head which is attached to each of these models. In the pre-trained head, it trains by predicting the masked values, and in the prediction head, it auto-regressively trains by predicting the next values. And the reason I mention this is because, again, in the GitHub, there are two ways of going about training and getting the results. Firstly, there is the pre-train approach, which the first approach is you first do a pre-training for some set number of epochs, where you are doing this reconstruction of masked patches. And after having a model which has been pre-trained on some data set, you then do fine-tuning or linear probing with the prediction head. So you first have the pre-train, which has been done on self-supervised approach, and the next step is you either fine-tune or linear probe. When I say linear probe, it means just trying to change the weights of the last few layers. So you're just trying to see if the last layer is what that needs to be changed in order to get good fine-tuning scores, or if you want to fine-tune the whole network. And the other way of training would have been an end-to-end supervised training approach with the prediction head. And the reason they do it in these two ways is because the paper shows that when you do have a pre-training followed by a fine-tuning and linear probe, it actually turns out to be computationally less expensive, because you almost remove the, I mean, you're pre-training it, so you have a benchmark model which can then be used for a wide range of generic tasks, maybe even across data sets. And they show that in this approach, where you pre-train and then followed by fine-tune linear probe, they're actually able to reach good enough mean square error and mean absolute error scores, even when you're doing supervised training end to end. So these are the two ways of training, and why the self-supervised and supervised approach makes sense here. This is just a little more on the model parameters. So this is the total number of parameters in this model. And something from the appendix that I figured I would just put here for reference is the fact that the patch TST essentially has 3 encoder layers with this many heads, 16. And the latent space that we saw was where there's a projection that is happening from here to here. It's actually 128. And yeah, they try on these data sets, ILI, ETTH, and um, yeah, with a dropout of 0.2. Some of the experiments that they try are, firstly, they have these data sets that they're working on. I've also just put this slide here so that we could, for future reference, if you want to see what the baseline experimental studies were, they essentially look at all of these baseline models with a prediction length ranging from this to this, so 24 to 60. And for the larger data sets, they look at something from 96 to 720, where I think the default in the paper that they're using is either 336 or 512. And they have two model variants, which I spoke about in the beginning. So they firstly have the patch THT 64, which implies that the number of input patches is 64. If we end up doing the math, if you have the look back window of if you have a look back window of 512, and you have patch size of 16 and stride of 8, and this basically means 512 by 8, which is 64. That is the number of inputs to the transformer, and this shows to have some good performance, which also suggests the title of the paper. And they also suggest another model which has 42 patches with a look back of the 336. So similarly, if you take 336 divide by the stride, which is 8, you end up getting 42, which is another optimal model that they suggest. So in this, I wanted to show the fact that um, I wanted to show the part where in the paper they mentioned the strategy for self-supervised followed by supervised training. So the ideal approach that they suggest is once the pre-trained model on each data set is available, we perform a supervised training to evaluate the learned representations with two options: one which is linear probing or end-to-end fine-tuning. Uh, with with linear probing, the idea is you only train the model head for 20 epochs while freezing the rest of the network. Whereas with end-to-end fine-tuning, you apply linear probing for 10 epochs to update the model head, and then you do end-to-end fine-tuning with the entire network for 20 epochs. This is just the way they've described their process of pre-training, linear probing, fine-tuning, and they show that this two-step strategy with linear probing followed by fine-tuning seems to outperform doing fine-tuning directly. Um, So these are some of the interesting benchmarks from this paper. It follows the previous structure where, in this case, they're doing the supervised training end to end. They with the patches, with patch GST 64, with patch GST 42, and comparing it with all of these other models, they see that it almost always ends up being the best scores. And this is something interesting because this is doing end to end supervised training. The the second set of results that they show is the one where they do the structure where they first do self-supervised training, pre-training, followed by linear probing, followed by fine-tuning. And in that case they show that with pre-training followed by fine-tuning and pre-training followed by linear probe, they're able to still achieve scores which are almost comparable, if not better, to scores of end-to-end uh, supervised training and across data sets. So this is weather, electricity, traffic. Um, the other more interesting results that they show is they do a pre-training on the electricity data set. So they do the self-supervised masking regeneration on this electricity data set, and then they try to fine-tune on completely different data, which is traffic and weather. And they see this whole they repeat the same process of fine-tuning, linear probing, and comparing it with end-to-end supervised, and they see that it again performs very well here as well. So this shows that in transfer learning as well, this is a very applicable approach where you do pre-training on any one of these supposedly robust data sets, and it's almost easy to apply it for any other data set with a little bit of fine-tuning and linear probing. Mm. So in conclusion, essentially, they've suggested an effective design of transformer-based models for time series forecasting by introducing two very simple components, which is patching and channel independence, which is a straightforward idea. And they compare it to previous work, and they see that because it captures the local semantic information, it benefits from the longer look back windows, leading to higher accuracy. And one of the main key idea that they say is, the fact that if you do self-supervised learning followed by supervised learning, it helps a lot in transfer learning. um, some other ideas that I just wanted to put out there after discussing patch TST are two of this, which is times FM and Chronos. These are some of the other state of the art work that have been released over the after patch TST. And these both of these work, times FM is by Google and Chronos is by Amazon, and both of these models essentially try to do pre-training on a large set of time points. So like they're saying here, they've done a pre-training on around 100 billion real world time points, and then they try to see if you can have these models that have been trained on all of these large sets of data, and then if you can do off the shelf zero shot learning performance on any time series that you want. So no fine tuning required, no linear probing, just it's been trained on a lot of data. Can you take it and then apply it for your time series task? And times FM and Chronos are trying to do that. Just wanted to highlight some results here so that it can give a connectivity to what the state of the art is now looking like. So in times FM, they try to see how it compares with all of this. It's not completely a fair comparison because in times FM you're comparing with all of these 100 billion data points, but in concept, without going too much in detail, times FM is also using something along the lines of what patch TST is doing. It's a derivation of patch TST, with a decoder only approach, whereas in patch TST you had a transformer with encoder decoder, whereas in times FM you're trying to do more of a decoder only approach, which is kind of similar to some of the state of the art in NLP. And in Chronos, it's a completely different approach where they're trying to do some scaling, quantization, and again, it's a zero shot performance where you've done a lot of training, pre-training on all of these 100 billion data points, time series data sets, and then trying to do predictions. And here, even their best case scenario almost works as good as patch TST. I think the best model of Chronos is slightly worse off than patch TST. And yeah, so these are two other key ideas, and I think a lot of other companies are also trying to make this process where they use their time series data to build a, 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 a good checkpoint which can then be fine-tuned, or it can be used as a off-the-shelf zero shot learning time series predictor. Well, that's about it. I can open it up for questions or any discussions on this topic.
So I'm a little confused, and I'm a little suspicious of what seems to be kind of a hyperparameter fitting that was suggested in the way you presented the paper, unless I misunderstood you, relative to sort of patch length and stride length and all of that. In that, seems to me that depending on the periodicity that might exist in a data set, you should see a high degree of dependence on that type of hyperparameter. And so do you suspect at all, based on your reading of the paper, that those particular hyperparameter settings are endemic or sort of a result of the data that they extracted empirical results with?
So you're saying all of these values, right?
Yeah, exactly. The patch sizes, all
Right,
of that stuff.
64, and
Yeah.
whether it's specific to the data set.
I mean, it would seem logical to me that it would be, right? Because if I was to throw, let's say, second by second, financial time series data versus day by day financial time series data, I would expect that, a different stride length and a different patch size should give me significantly different results. If you will, the language that's being predicted there for short-term time series and finance versus long-term would be completely different. And by extension, I'm not familiar with the data sets that they used for training, but I suspect that, I mean, given that it was weather and traffic, that the kinds of data that are in there tend to be sort of long form.
Yeah, it's not just across seconds.
Right.
Yeah.
There could be periodicities in there that are related to the rotation of the Earth around the sun, right? And so these particular patch lengths and these particular hyperparameter settings are really specific to a data set of that type. Do you have any suspicions of that type of that form?
I think they also, I mean, yeah, you may be right, because even here they mention that, right? I think they say that a prediction length of this much works for ILI dataset, which happens to be a smaller dataset with, I think, smaller time series than the others. So I mean, I think if you have larger data sets which span across a larger time series, like these other ones, they seem to be using a much longer look back.
Yeah, I'm
But
surprised that these time series efforts um, have not attempted to transform data into the frequency domain in order to, in a way, eliminate some of these questions of periodicity and and scale, if you will, right? Because you could have periodic patterns in a data set that scale very differently depending on the type of data that you're throwing in, and so we might want to learn that periodicity is a thing, and it's potentially much easier to detect in the frequency domain.
Right.
That's an interesting point, Andrew. Bringing it into the frequency domain.
Yeah.
And we talked about it. Wasn't that paper that Asif that was 2 weeks ago? That possibly is also could be applied here too.
I mean, it's entirely possible, given the representative theorems, that that's exactly what these models are doing, right? That they're transforming the data into a frequency representation and then performing predictions on that basis somewhere deep inside the model. But I wonder what would happen if you presented data cleanly in that space to begin with.
So what you're saying is that with the layers, it's actually in the latent space. That's exactly what is happening. It's figuring out its periodicity and a little bit of perturbations, the longer periodicity and some perturbations, and probably that's what it comes up with in the latent space to predict the next set of data.
Yeah, that's what I'm getting at. Exactly.
Right.
Actually, the Times FM, which is the Google's paper, it is continuing on the same approach. So they are also not going into frequency domain. So maybe there is a reason why sticking to the time domain
No, I think
helps.
what Andrew was saying is that internally in the latent space,
Yeah, it's
that
possible.
is what might be
It is
happening.
possible that it is happening. But I'm saying Times FM doesn't convert it into frequency domain also to feed it into the transformer. Times FM is a very recent paper, which is by Google, which is using the patch TST framework, but even that is not converting it into the frequency domain. It's possible that internally the transformer is doing it because of the training. I mean, the way it gets trained, it is possible.
Sure, I understand. I guess I'm perplexed as to why, given that time series are so clearly able to be transformed into the frequency domain, why the researchers don't even mention that or explore that.
Andrew, may I hazard a guess here?
Yeah, please.
Obviously, I'm an expert into this domain. See, what happens is if you were to do a frequency domain transformation, then you would be looking at a spectrogram. Because you would say at any given time window or time slice, these were the frequencies observed. Then, given a spectrogram, it becomes a vision problem, computer vision problem. So, for example, in audio, you do that. And I suppose for audio and for a time series signal, people have some technologies or have tried to predict in the past using the spectrogram. Now, the advantage, I suppose, in the time domain, the disadvantage you pointed out correctly, I think you're right. It does become sensitive to the hyperparameters, but it doesn't become a real issue for one reason. See, if you look at real time series data, for example, coming out of our equipment, the 64, their patch size is 64. Whereas if you take something like sound, which is going at 64 kilohertz, you realize that this patch is very tiny. And so the hyperparameters, though theoretically they matter, the stride length and so forth, and the patch window size, they are relatively epsilon compared to the time, the actual, even 1 second, the data coming in for a given second. So you're already looking at a millisecond sort of a time slice. That is what. The other way that I would like to intuitively think is, suppose this window, so let's say that you ate the vector in 4 dimension. Imagine that it were in 2 dimension. What you're doing, and the reason transformers would find it very intuitive is, it is just basically asking, what is the trajectory this vector is making over time? And that is a lot easier to figure out if you treat each vector, because it's an embedding space vector. One would say that whatever position it will next take is in the very proximal neighborhood of the position that it is on as a vector point. And I think something that intuitive or physical intuition may be the reason why working in the time domain is more effective in these situations.
Sure, that makes sense. And to your point, clearly when you transform into the frequency domain, you're implicitly, predicting the future of the waveform because each element in the frequency domain is an infinite extension, right, of that component. And so when I say transform into the frequency domain, I'm imagining that there would be some patch length and some stride, and you're doing a finite Fourier transform on each of those patches as as you move them forward in the time series. And now what you're predicting really is how the frequency components are changing as opposed to what the next specific time domain element looks like. I don't want to belabor the discussion with this. It's just a musing of mine as to why the researchers don't even sort of mention this concept.
Yeah, but I have seen people do spectrogram-based prediction. For some reason, there isn't too much activity, and I've thought a lot about it. The closest that I could come to is the guess that I made.
Actually, Lavanya has shared a paper, so maybe we should look at it. I mean, for later. She has shared a paper in the chat.
Okay, yeah, I don't want to belabor the conversation with this topic. It was just thank you, and it's up to you if you want to keep talking about it.
Any more questions, guys? Oh, guys, so first of all, Shrikant, thank you for this wonderful presentation. And it's really, really wonderful that fairly, when you have just entered this topic so quickly, you have reached the state of the art, the state of research, and you could summarize it and cover this paper. I do know that this paper sort of is a historical landmark. It's perhaps one of the first time that a transformer model actually worked for good time series prediction and beat the linear models, as you pointed out. So it does represent a historical milestone, and it has lived the test of time. The state-of-the-art models still are close in performance to this model. And thank you again for this awesome presentation. And guys, if you do have any other questions, please do ask. Then I want to mention something that Andrew wrote, which relates to the topic of last week, but I'll come to that. But let's first take questions on this topic. Oh, not many questions. All right, folks, one of the interesting thought or perspective articles that Andrew here, who's here.
If you're still recording it, that's
yeah.
okay.
Wrote is he posted it on LinkedIn, and I posted the link on our Discord and also on the chat. I invite you to read it. It's a very interesting. I found it very interesting. I just finished reading it. A thought on what happens when AI agents meet each other on the internet.
Yeah, if I may interject, I just had a thought when I was running down the coast the other day after listening to the very nice presentation last week. And it occurred to me that, we have a myriad of interfaces, sort of by definition, the interface of the internet is directed at human beings. And we now have agentic systems that understand natural language, which is an encoding for knowledge that can encapsulate basically the entirety of human experience and human knowledge. As we release agentic systems into this space that has all of these interfaces intended for humans, and these agentic systems can now connect to those interfaces and interact with them, we are surely going to find a scenario where two of these agents find each other, and they will then begin to interact with each other. And in this piece, I whimsically explore what could occur. But I also, through that whimsical exploration, realize that we've entered a phase of the internet in which all of these interfaces that were previously meant for human beings are now accessible to machine exploitation in ways that that extend way beyond the kind of sort of botnets that flood chat rooms with hate speech or do any of that kind of sort of population level attacks, or gaming, music streams for payments to particular music producers. We now have a scenario where those human level interfaces can become APIs by which information can be exfiltrated. And so I fully explore that, or at least partially explore it in this piece, and I intend to follow up with it.
Thank you, Andrew. All right, folks, I'm about to stop recording. Anybody after that?